Good morning. Welcome to Krishna's class. We continue with our exploration of Lebesgue integration. In fact, last we concluded Lebesgue integral of bounded measurable functions on sets of finite measure. So that is one stage of our process. Now, before we go for further general scenario, it is interesting to probably recap what we did so far very quickly and just retrace the path. Of course, our objective in the beginning was to give a rigorous formulation of integration. The first step was to introduce what is called Riemann integral. Riemann integral gave a very satisfactory explanation of integration for a large class of functions. However, we called this, however, this had some limitations. First of all, Riemann integrals were defined for real valued functions from compact intervals a b to r, which are in fact we attempted to do that, not necessarily all bounded Riemann integrable functions from compact intervals are Riemann integrable. Okay. So we got a class of functions which are Riemann integrable. Of course, RAB was not equal to the entire class of bounded real valued functions defined on the compact interval. Okay, so it's a subclass of that. Now, this, of course, we analyzed further for all its shortcomings, and the shortcomings pointed to the need to go for a generalization. Okay, so shortcomings called for generalization. So first we should try to understand what are the salient features of this defining Riemann. Worked on partitions were of AB led to the so-called simple so-called step functions. And integral was defined for step functions. Then of course we introduced what is called the upper integral and lower integral of a function of this class. Okay, so we introduced the concept of upper and lower integrals. Of bounded real valued functions on compact intervals A. Now, then we said that the function is Riemann integrable if the lower integral and there exists functions which are bounded and real valued where the equality of this lower integral and upper integral cannot be assured. So, Dirichlet function a simple example of a function which is not Riemann integral. So, not all bounded functions were Riemann. That is it. So, the Dirichlet function, give example, the Dirichlet function was although it is bounded and real. Okay. And there were so many other shortcomings which we had explored in detail. So, we went to the next step of rectifying this. The next stage was introducing concept of measure called the Lebesgue measure. For subsets of R so there are subsets, and so this is called the Lebesgue measure. Lebesgue measure of any measurable set we put it this way, all intervals are all intervals are and measure of an interval is so what we called the Lebesgue measure of all measurable sets is a credible generalization of the concept of length. But now it is available for a wide class of subsets which you call the measurable sets. Okay. But not all sets are measurable. There exists subsets of R but the measurable set satisfied some of the requirements that we were asking for, like translation invariance, and if a set is measurable, then its complement is also measurable. The empty set is measurable, and it's a countably additive set function. Measure is a countably additive set function, etc. So all those properties were satisfied. They were all desirable properties, but then the sacrifice that we had to make was that it was not available for certain sets. Okay. Now, so having got these measurable sets, we defined what are called measurable functions. So we introduced what are called measurable functions. To go to the definition, simply says that the inverse image of intervals are measurable sets. That is the definition. Then we found that all reasonably nice functions are measurable, like continuous functions are measurable. Okay. So we have a huge class of functions already. Remarkable. All continuous functions are measurable. So it's already a huge class, okay, but it's much larger than the class of continuous functions. Okay, but not necessarily all bounded functions are measurable, because that has something to do with the existence of what are called non-measurable sets. Okay. For instance, the characteristic function of a non-measurable set is not measurable, but this one is essentially a bounded function. So not all bounded functions are measurable, but you see that still it's a huge class of measurable functions. Okay, then we introduced, so the next stage was we defined what are called simple, which generalizes step functions. See, the difference between this is that step functions are related to intervals, whereas simple functions are related to what are called measurable sets. Okay, so we go to the definition and compare the definition, and you know that all step functions are simple functions. Now, what else? We introduced integral of measurable functions, sorry, of simple functions. It coincided with the Riemann integral of step functions. Riemann integral of step functions. Then you recall what we did in the case of the, the or while defining Riemann integration, what did we do? We approximated from above and from below with step functions, and then we introduced what are called the upper integral and the lower integral, and when they were equal, we said it is Riemann integral. We take a similar approach. Okay, right? The next step was approximations of course. Next step was considered what are called bounded measurable functions on sets of finite. Functions on what we did was we proved that the existence of approximations of such functions by simple functions. Therefore, what could we do? Using this fact, we introduced upper and lower integrals bounded measurable again. We did exactly as in the case of Riemann integration, and we said and lower integrals are In fact, we proved that all measurable bounded functions defined on measurable sets of R integral. Therefore, we successfully defined Lebesgue integral for bounded measurable functions defined on sets of finite. Okay. I found that for all Riemann integrable functions on bounded intervals, defined on bounded intervals, we proved that the Riemann integral coincides with the integral, that is the Lebesgue integral. Therefore, Lebesgue integral is a legitimate generalization of Riemann. So for integrable and Riemann integral of the Riemann integral and Lebesgue integral coincides, assuring that Lebesgue integral is a generalization of Riemann integral. Now, this is what we have done so far. And then, of course, we considered all the properties of Lebesgue integration, etc. The detailed discussion on that. Several theorems were proved in this regard. And that is the path we have traced so far. So, our journey is still not complete. You recall that what we have looked at is the following. Talked only about bounded measurable functions and on sets of finite measure. Okay, so we want to now get out of these constraints. Go further by what you call dropping the by to consider unbounded measurable functions on sets of infinite measure. So that's our next task. So that's the title, but we have brought in a extra term here, condition here, saying non-negative functions. So it needs certain explanation. So we have to go through step by step. We begin with, we consider in this stage at this stage measurable non-negative functions. Non-negative on measurable sets. There is a reason for this. So we put the additional restriction at this stage that we consider only non-negative measurable functions on measurable sets. Okay, we get rid of two conditions but bring in, so that means go beyond bounded and further beyond go beyond this and go beyond bounded measurable functions. However, we assume non-negative. Need some explanation why we need it. So let us see why. There's a reason for this. then only we can go to the next stage. Our strategy is to write any given measurable f as the difference of two non-negative measurable functions. This we have discussed earlier. What is it? That is, f we write as okay. When you recall what it is, suppose you have a function whose graph is like this, then your this is your f plus, this is your f plus, and this is your f minus. This is your f minus. So f plus is maximum of which you know is f minus x is maximum of minus fx, which is again positive. And we also have the relation that f is equal to f plus minus f minus. Then we plan to get and integral f yes, they may be infinite. Infinite. So you see, when we write and then write now there is a problem. Now there is a problem. What is the problem? If both integral f plus and integral f minus are infinite, then this is not It's possible that integral f is infinite. Okay, that is no problem. It may be finite or infinite. But certainly, if these two are both simultaneously infinite, then integral f is not. Note that if both infinite, I mean they are going to be positive plus infinite. To remember the calculus, we have extended from real number system to R star, which includes both plus infinity and minus infinity. Okay, we had the usual rules for addition and multiplication. In addition to that, we defined a plus infinity equal to infinity, that is a plus a minus infinity equal to minus infinity for every a belonging to R. Then we had a into infinity is infinity, a into minus infinity is minus infinity. There is no problem with that for every a. Then we wrote, for our purpose of this integration theory, we also set 0 times infinity equal to 0, and this was a very crucial. So we had these kind of things, 0, then you had infinity plus infinity, but then the problem was this: when you had infinity minus infinity, this was not defined. So we will end up with a situation of this kind here. Okay, so when you talk about without non-negative, see, if it is, if f is non-negative, then you see that integral over f equal to integral over f plus, that is plus infinity. The other part is going to be 0. There is no problem, it is well defined. Okay, but it's not defined if both integral f plus and integral f minus are negative. So what we do is, for the time being, so at this stage, we assume f is at least almost everywhere except on a set of measure 0. Okay, right. And for that, we develop what is called the Lebesgue integral. What is the strategy? The strategy is to exploit whatever we have done so far, because you know that we have come up to the stage of defining Lebesgue integral of bounded measurable functions on sets of finite. As I said, there are two problems here. The function itself may not be bounded. The set also may not have finite measure. So what you do, you try to approximate the given measurable non-negative function by functions which are bounded measurable, of course, obviously non-negative functions on sets of finite measures. So, two types of approximations creep in. One, the function that we choose is going to be a measurable function. It's obviously when we are going to approximate, we are taking non-negative function, then it's going to be non-negative measurable functions. Okay, and we want to do it from below, and we want these functions to be bounded. So we are now going to trying to approximate measurable non-negative functions by bounded measurable non-negative functions from below, okay, defined on sets of finite measure. There are two things here. One is the domain of the function need not be, of the given function need not be having finite measure. Therefore, we will have to do some approximation on that part. Then the function that we are given may not be bounded. Okay, so there again we will have to do some approximation, but we have certainly kept this is non-negative for the time being, because I'll just give you the reason for this. Okay, now we have at the next stage we have to be cautious, and you see that f measurable implies mod f is measurable. And mod f is measurable means what? And therefore, you can talk about, after having developed the integration theory for this, you can look at this possibility, whether this is integrable or not. How will you define this? This will be, because mod f is going to be defined as, is going to be, both are non-negative functions. Now you can easily write this as, there is no problem, because this is plus infinity, this is also plus infinity, both are plus infinity, their sum is going to be plus infinity. If one of them is plus infinity, then it is going to be infinity. So we are not bothered about the integral becoming infinite, but we don't want uncertainties of this kind. Okay, so such functions we will designate as integrable functions. That means okay, so we can work on this one, and if this is well defined, even then it is not clear whether this is well defined. Okay, so that's the problem, right? So at this stage we assume f greater than or equal to. That's our task. So I gave some idea of which way we are going to. So our task is now to approximate both the domain as well as the function. The function is a non-negative function which we try to approximate by bounded non-negative functions. So let me be here. Okay, so we approximate it from below by bounded measurable functions on sets of finite measure for which the theory is already available. So we are free to make use of this. And then what you do is you take the supremum of all such possible approximations from below. Okay. Right? Call that the integral of the given measurable function is non-negative. Okay. Right? So that's the strategy. So let us now start working on this. Now for that we need some preparatory work. Like we need to introduce some new terminology. A measurable function f on t is said to vanish outside a set of finite measure if there exists E naught measurable contained in E with finite measure is and f is equal to 0 on, that means the complement of E naught, the function is identically 0. Okay, so we define a terminology, support of f, set of all x belonging to E for which measure of and finite. Okay. Function with a the finite support. So the set on which f is not equal to 0 is what you call the support of F. Measure of the support of F is finite, then we say F is a measurable function with a finite score. So we'll use this terminology, and when we use this terminology, it simply means that these two conditions are satisfied. Okay. So we start talking about what are called bounded functions with a finite support. Okay. So we shall bounded functions now you know that for these functions integral is different, and we can apply the whatever we have done until now for these functions. For such functions, integration is different. Integral is different. Okay. And we defined as integral over F. This is equal to integral over dot F, where E naught is the support of now you see we should not confuse with the concept of support topological in the topological sense that we are used to. So you take a real valued function on R, we say that the function has support. In that case, we defined the support as the closure of the set on which the function is not equal. It's a closed set. So remark the topological context support is a closed set. And since support of F equal to the set of all x not equal to 0 and the closure. Yeah. Where so that aspect is not coming because at the moment we are not bothered about topology. Although on the real line we have the the topology, the natural topology on that, and all the open sets are measurable sets. In fact, the measurable sets that we have defined, okay, so what you have is, it's a larger class of sets. Measurable sets are a larger class of sets. Now what we ask for in this case, we write M, the support of F is the X belonging to, or which Fx is simply not C, not in this sense. Now how does this integral come? See, you have integral over E F can be written as integral over E naught and what you have is this part is 0. That's how this comes. Well, this is not, we have not defined all these ideas very precisely, but this is how it comes. So on E slash E naught, you are going to have F equal to 0. Therefore, this integral is 0. It doesn't matter. So E slash E naught may have infinite measure. If E naught is measurable, E slash E naught is measurable. That is what you are doing is you are writing F as F into chi of E naught plus F into chi of E naught. Okay, depending on E, measure of E slash E naught may be infinite. Okay, then what do you write as this? So this is the integral. Therefore, you see that integral over F equal to integral over E F chi E naught plus integral F chi is the characteristic functions and over, and that essentially leads to this one. Okay, and E slash E naught, see, this is what happened. This part will be, see, this part if E naught is the support of F, then and integral F this is going to be integral of 0 and this may be infinity, but then 0 into infinity is taken as 0. Okay, and this is equal to 0. Whether finite or infinite. So this is how we define. Now we are in a position to define what is called the integral. So we define the integral. So we let measurable non-negative functions. Okay, so let us define this. Now we this is equal to the supremum of integral over h, where h is bounded measurable with finite support and 0 less than or equal to h. So you take all functions h which are bounded measurable functions with a finite support. That means the support of fh on E is if it is given by E naught, then measure of E naught is finite. Okay, right? And we also want this function to be squeezed between 0 and f. So it's a non-negative function which is bounded above by f. Okay. So for such functions, now you can define what is integral over E h. That is well defined. Okay. Then these are all numbers. Okay. They are all non-negative numbers, not necessarily bounded, because it depends on whether the function f itself is bounded or not. It may not be bounded at all. Okay. Now you see that this is if it is bounded, if this set this 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 collection of numbers is bounded, then you have the supremum as a finite number. If it is not bounded, then it becomes plus infinity. It's measurable. It's non-negative. With finite support. Is bounded above, then its supremum is the upper bound, the least upper bound. Supremum of X's. And that and this is called integral of f over, and this and is fine. If it is not bounded, so let us look at some examples. So let me take some examples. First example. Okay. B as okay. Now, or including this one, it's a bounded set. Now take fx then in this case what you see is the function, the graph of the function is this. So this is a case where measure of E is finite. Is finite. Now what you have is, this is the graph of the function. unbounded. It's an unbounded function. But measurable. F is measurable. Okay. So it's a measurable unbounded function, and you see that this can be approximated by functions of this kind. This is a typical. What I have drawn here is a typical approximation. So some h. This I write h. So integral over h is defined. Take the supremum of this. You see that the integral is for each h is a finite number, but it's not the whole collection. For the whole collection, it is not finite. So here you see that the integral a similar situation can arise. So you take one to infinity, define fx to be equal to 1 by x then once again you can approximate this function. Function is something else. Here you can approximate it by a integrable function. There are several functions of h of which approximates it from below, and you see that the integral that you have is not bounded. Once again, here measure of but the function is a bounded function. So even if the function is bounded, integral may be infinite. Even if the function, the domain is bounded, the function may have infinite. Okay. Now a third example that is probably interesting to look at is this. Consider this function. Now you see that the graph of the function is this reflection here, and at this point it is 0. The value of the function is 0 here. This is the graph of it. Now you see that integral over f plus integral over f minus is also, so integral over f is not different. that example view. And that's a very interesting example. So I think I will conclude this talk at this stage and then get on to work on the properties of the integral. So we have already defined what the integral is. Okay. Now we start working on the tools to give a very rigorous discussion on these topics. These are not rigorous, but then one example which I have considered, which you are familiar with, and looked at the properties. Okay. Thank you very much.